let ABC be a triangle such that angle ACB is equal to pi over 6. Let me draw it. So that's A, B, and C. A, B, and C. And they tell us that angle ACB, this angle right over here, is pi over 6. I'm assuming it's pi over 6 radians. Or we could view that as 30 degrees. And then they tell us, let A, B, and C denote the lengths of the sides opposite to A, B, and capital A, B, C, respectively. So this is A, this is B, and this is C right over there. The values of x for which A is equal to this thing, B is equal to this thing, and C is equal to this thing is. So let's think about it. One, we need to find a relationship between A, B, and C in this angle. And then once we have that relationship, we can substitute them with these expressions and then essentially try to solve for x. And the first thing you want to think about is, OK, how can I relate the length of B, this lowercase c, this lowercase a, with this angle here? And what should pop out into your brain is the law of cosines. Law of cosines. Law of cosines that tells us that c squared is equal to a squared plus b squared. It's essentially the Pythagorean theorem with an adjustment right here, because this isn't a right triangle. So a squared plus b squared minus 2ab times the cosine of c. Now, in this case, angle c right here, or I should say angle, in this case, it's angle ACB. This over here is going to be 30 degrees. So what's the cosine of 30 degrees? And just in case you forgot it, although I assume if you're going to take the IIT exam, the JE, you're going to need all the help you need in terms of time. So if this is 30 degrees, that is 1. Then this is 1/2, the side opposite the 30-degree side. This will be 60 degrees. It's going to be a 30, 60, 90. And so this is square root of 3 over 2. Cosine is adjacent over hypotenuse. So it's square root of 3 over 2 over 1. So this, in this example, is going to be c squared is equal to a squared plus b squared minus 2ab. And then this whole thing is square root of 3 over 2. So times square root of 3 over 2. And these 2's cancel out. And so we get c squared is equal to a squared plus b squared minus the square root of 3ab. Now, the next thing I'd want to do is substitute for A, I'd substitute with this expression over here. For B, I want to substitute with this expression over here. And then for C, I want to substitute this expression right over here. But I want to be careful. I want to make sure that it's in a form that I can in some way simplify. Because if I just take this A over here, this x squared plus x plus 1, if I square it, I'm going to end up something to the 4th power. This B, I'm going to end up with something to the 4th power. And then I have the square root of 3 business over here. So let's see if we can at least rearrange it, or at least maybe quarantine the square root of 3 a little bit to make it at least something that we might have some hopes of factoring or solving in some way. And I want to make a little clarifying point here. In most Western exams, if you're taking the SAT or you're taking any type of, even at a math competition, if you find yourself grinding through math, multiplying huge polynomials times each other, you're probably doing something wrong. Most Western exams, like the SAT, you kind of have to see the trick. You kind of have to see the elegance in the problem. But once you see the elegance, the problem is usually pretty straightforward. In fact, if you're grinding through math, it's usually a giveaway that you're doing something wrong. On these JEE math problems, and I've only recently gotten exposure to them, I obviously never took them, not having grown up in India. But on these, you have to kind of see the trick, and then you have to grind through math, and you have to use every trick at your disposal to make the grinding through math a little bit easier. So the test writers for the JEE are definitely actually a lot more cruel than the test writers for most Western exams that I've seen. So what I want to do is let's just isolate the square root of 3ab. So let's add it to both sides. So square root of 3ab. Plus, so let's just add that, square root of 3ab. And let's get the c squared onto this side of the equation. So let me subtract c squared from both sides of the equation. So minus c squared, and then minus c squared. And so I will have, on this side, those cancel out. And I just have the square root of 3ab is equal to a squared plus b squared. These cancel out, minus c squared. I'm just rearranging the whole thing. Minus c squared. All of that Well, right now that's all it is. And now I can divide both sides of this by AB. So if I divide that by AB, and then I divide the right-hand side by AB, that cancels out. And I've kind of quarantined that square root of 3. So I'll hopefully only have integer stuff on this side of the equation. So I have the square root of 3. The square root of 3 is equal to a squared plus b squared minus c squared. So let's figure out what each of these things are. Let's expand them out before we rewrite it. So let's figure out what a squared is. So let's think about a squared. A squared is going to be equal to, and this is the part where they clearly want to see whether you can multiply multiple polynomials. That's going to be x squared plus x plus 1 squared, or x squared plus x plus 1 times x squared plus x plus 1. And so this is going to be 1 times this whole thing is x squared plus x plus 1. X times this whole thing is x plus x squared plus x to the third plus x to the third. And if you may or might have noticed, I'm doing these a little faster than I traditionally do them, just in the hope of being able to finish this problem in a reasonable amount of time. And then finally, x squared times this whole thing. X squared times 1 is x squared. X squared times x is x to the third. And then x squared times x squared is x to the fourth. Is x to the fourth. So a squared is going to be x to the fourth plus 2x to the third plus 3x squared plus 2x plus 1. So that's a squared. What's b squared? That looks a little bit more straightforward. B squared, so that's b. So b squared is going to be, well, that squared is just x to the fourth minus 2x squared plus 1. And then c squared, that's more straightforward. So at least they weren't as painful as this. C squared is going to be 4x squared plus 4x, 2 times the product of these two. So plus 4x plus 1. So the numerator of our expression here, so let's rewrite this thing that we were simplifying. It now becomes the square root of 3 is equal to, oh, and we don't want to, well, let's just do one step at a time. So it's equal to a squared, which is this thing over here. So it is x to the fourth. Actually, let me scroll down a little bit. It's this thing plus this thing minus this thing over here. So let me just do it. It's this thing plus the blue thing plus x to the fourth minus 2x squared, It'll be easier to add them up this way, plus 1. And then it's minus this thing, minus c squared. So this is going to be minus 4x squared, minus 4x squared, minus 4x, and then you have a minus 1. And then when you add them all up, so this will be the numerator of this expression. We have the square root of 3 is equal to, so let me just do it down here. So you have 2x to the fourth. Scroll to the left a little bit. So we have 2x to the fourth plus 2x to the third. And then 3x squared minus 6x squared is minus 3x squared. 2 minus 4 is minus 2x. And then you have 2 minus 1 is, and then you have just plus 1. So the numerator, this thing over here, simplifies to this. It's equal to 2x to the fourth plus 2x to the third minus 3x squared minus 2x plus 1. And the denominator is AB. A is this thing over here. A is x squared plus x plus 1. And b, we saw it up here. B is, actually, we have it written up over here. B is x squared minus 1. So b is x squared minus 1. Now, at this point, we need to solve for x. If we just multiplied this stuff times square root of 3 and went backwards, kind of unsolved it back to the form that we had way up here, we'd have a 4th degree polynomial with square roots of 3's in it. We still have a 4th degree polynomial. But at least this one has all integer coefficients, which at least gives me some hope that I might be able to factor it. I might be able to find some roots. And if I can find some roots that are common to the numerator and the denominator, maybe I can reduce this into a lower degree problem. So I'm going to leave you there. I'm pushing 10 minutes. In the next video, we're going to try to factor this beast up here and see if it has any common factors with this over here, and then try to solve for x. Welcome back. Where we left the last problem, we essentially found ourselves having to solve this equation right over here. And where we left off, we said, well, maybe, just maybe, we might be able to simplify this a little bit if we can find some common factors between the numerator and the denominator. And I want to do it here because if I multiplied this out and multiplied it times the square root of 3 and then subtracted or added to that so that I got just a straight up polynomial, that polynomial is going to have the square root of 3 in it. It's going to be a really, really messy thing. And it's still going to be fourth degree. And at least this way, I have some chance of being able to solve it. At least I just have integer coefficients over here. And the only way that this is going to simplify is if it has any common factors with the stuff down here. And when you look over here, this right here is actually going to have complex roots. If you did the negative b plus or minus b, the square root of b squared minus 4ac over 2a, the b squared minus 4ac over here is actually going to be negative. So it's not going to have any real roots. So that is not going to have any easy real roots. But this is the x squared plus 1. That has x plus 1 and x minus 1. Or another way to think about it is roots to this are negative 1 and positive 1. So if either of those are roots to this, then we're in business. And actually, just looking at this, there's a decent chance, because in general, if you want to think about the roots of well, really any nth degree polynomial, the roots, if you think about it, let me just draw it over here. If I have a bunch of roots, x minus r1, x minus r2, x minus r3, and then let's say we have a fourth degree, x minus r4. So let's say we have 4 roots. When you multiply this whole thing, you're going to have x to the fourth plus blah, 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 all the way. And then the last term over here, is going to be r1, r2, r3, r4. It's going to be the product of all of these. And so if you wanted to put this equation right, or this expression in this form, you divide both sides by, or divide the whole expression by 2, or you can kind of say, well, let's just look at this thing and divide it by 2, and then you would have x to the fourth plus 2x, all of that, plus 1/2. And so this thing would have to, in this context, be equal to 1 over 2. And a way, this is kind of it's not a fail-proof technique, but it is one way to kind of discover roots, is you say, okay, the roots could be the factors of this divided by the factors of that. And 1 is definitely a factor of both of those. And actually, if you think about it, negative 1 can be as well. So we feel good. But let's actually try it out. Instead of going through all of this argument, let's actually see if either 1 or negative 1 are factors of this thing up here. If they're not, then we just have to move ahead, and if you multiply this thing out, multiply it by square root of 3, and then just solve. But we can hope. Usually the test writers aren't that big sadists. Otherwise, it wouldn't be that. It would be impossible to solve. So I'm feeling good about this. So let's just try it with 1. So if we try 1 here, so let's put 1 here and see if we get 0 over here. So if we get 2 times 1 to the fourth plus, so let me just write that. So 2 times 1 to the fourth is just 2, plus 2 times 1 to the third is just 2, minus 3 times 1 squared is just 3, minus 2 plus 1. So this is 4 minus 5 plus 1. That indeed equals 0. And let's try negative 1. Let's try negative 1. So this is 2 times negative 1 to the fourth. That's still 2. Plus 2 times negative 1 to the third. So that's negative 2. Minus 3 times negative 1 squared. That's negative 3. And then minus 2 times negative 1. So it's plus 2 plus 1. So this is 0, minus 3, plus 2 plus 1. This also cancels out. This also gets us 0. So we now know that both x plus 1 and x minus 1 are factors of this thing up here. Or another way to think about it is their product is a factor of this thing up here. X squared minus 1 is a factor of this. So if we were to divide x squared minus 1 into this, we should get a reasonable answer. We shouldn't get a remainder, I guess I should say. So let's do that. So we're going to get a little practice doing polynomial long division. So if we divide x squared minus 1 into this thing up here, 2x to the fourth plus 2x to the third minus 3x squared minus 2x plus 1. So this is good practice on polynomial long division. Highest degree term going into highest degree term. X squared goes into 2x to the fourth, 2x squared times. So let's put that in the 2x squared spot. 2x squared. 2x squared times x squared is 2x to the fourth. 2x squared times negative 1 is negative 2x squared. And now let's subtract this from up there. So let's or multiply it by negative 1 and then add it. And so this gives us 2x to the third, negative 3 plus 2, so it's minus x squared, minus 2x plus 1. And then x squared goes into 2x to the third, 2x times. So this is plus 2x. 2x times x squared is 2x to the third. 2x times negative 1 is negative 2x. And then we can subtract this from there, or you could say add the negatives. Let's just add the negative. It's easier to keep track of things. So those cancel out. You get negative x squared. These cancel out plus 1. X squared goes into negative x squared minus or negative 1 times. Negative 1 times x squared is negative x squared. Negative 1 times negative 1 is positive 1. And indeed, we get no remainder. So we can write this thing up here. We can write it as the product of this. So it is equal to, so this thing we can rewrite as 2x squared plus 2x minus 1 times x squared minus 1. So this times this is equal to this. So times x squared minus 1. So we just factored it. And so that simplifies things a good bit. It doesn't make it trivial, but it simplifies things a good bit. So now we can cancel that with that. And now at least we have things in second degree. We got rid of these third and fourth degree terms. So let's now rewrite things. So now let's multiply both sides of this equation by x squared plus x plus 1. So we're going to get the square root of 3. So let me just write it out. So I'm going to get the square root of 3 times x squared plus the square root of 3 times x plus the square root of 3 times 1. So I just multiplied the left-hand side by this, what we have left in the denominator, is equal to what we have left in the numerator. Because if we multiply the right side by this, it obviously cancels out. So this is going to be equal to 2x squared plus 2x minus 1. And now, if we want to, so let's now put this, now let's see what we can do here. Well, we can subtract these from, we can subtract the stuff on the right side from the left-hand side. And so we would get the square root of 3 minus 2 times x squared plus the square root of 3 minus 2 times x, just subtracting this stuff from that side, plus the square root of 3 plus 1. Right? Did I do that right? Square root of 3, I subtracted the x squared from that. So square root of 3 minus 2, square root of 3 minus 2. And then you have the square root of 3 subtracting a negative 1. I get a plus 1 over here. And since I subtracted all of this stuff from both sides of the equation, this is just the left-hand side. The right-hand side is now 0. I subtracted this from the right-hand side to get 0. So now we have, this almost looks ridiculously simple, even though I have these ridiculous radicals and all of that. I have a straight up quadratic equation right here. So I can use the quadratic formula. So the roots here, so x is going to be equal to negative b. This is b right here. So negative b, you can swap those. So it's 2 minus the square root of 3 plus or minus b squared. So let me just write it here. So square root of 3 minus 2 squared minus 4 times a. So that's the square root of 3 minus 2 times c. Well, c is the entire constant term right over there. So it's times square root of 3 plus 1. All of that over 2a. All of that over 2a. So all of that over this business over here. So that's 2 root 3 minus 4. So we thought we were in the home stretch, but now we have to do some major radical simplification. So once again, these test writers are not pleasant people. So let's try our best to tackle this. So let's go inside of the radical right over here. Let's go inside of the radical right over here, and you have the square root of 3 minus 2. Actually, you know what? I'm going to leave you there. I'm approaching 10 minutes, and frankly, I need a drink of water. This problem is maybe the most tiring problem I've ever done. I'll leave you there. We just have to simplify this in the next video. So I'm looking forward to the end of this problem as much as I'm guessing you are. And I think we're in the home stretch. We just have to simplify this to get the possible values for x. So let's simplify what we have here in the radical. So let's say square root of 3 minus 2. That's going to be square root of 3, and we're going to square this whole thing. That's going to be square root of 3 squared, which is 3, minus 2 times their product. So that's minus 4 square roots of 3. And then plus 2 squared. So plus 4, and then we have minus 4 times square root of 3 times square root of 3 is 3. Square root of 3 times 1 is plus the square root of 3. And then negative 2 times square root of 3 is negative 2 square roots of 3. And then negative 2 times 1 is negative 2. So this is going to be equal 3 plus 4 is 7 minus 4 square roots of 3 minus, so let's see, this 3 and this negative 2 over here, that becomes a 1. So that becomes a 1. And then the square root of 3 minus 2 square roots of 3, that just becomes a minus a square root of 3. So that just becomes minus or negative square root of 3. My brain is starting to hurt. So you have a negative 4 times 1, so it's minus 4. And then a negative 4 times negative square roots of 3, so plus 4 square roots of 3. And thank God, something has finally simplified here. And so this is, that cancels out with that. And so you have 7 minus 4 is equal to 3. So the whole thing under the radical sign is the square root of 3. So then this becomes our potential values for x. X is equal to 2 minus the square root of 3 plus or minus the square root of this thing, which simplified to the square root of 3 times the square root of 3. All of that over 2 square roots of 3 minus 4. So let's try to see what our answers could be. If we add a square root of 3, so one answer is if we add the square, if we go with the plus option, this would be 2 minus square roots of 3 plus square roots of 3. So it would be 2, the square roots of 3 will just cancel out. 2 over 2 root 3 minus 4. Divide the numerator and the denominator by 2. And we get 1 over the square root of 3 minus 2. And then to rationalize this, we want to multiply it times the square root of 3 plus 2 over the square root of 3 plus 2. We do that so that when we take the product here, it takes the form b squared minus a squared. So this is equal to the square root of 3 plus 2, all of that over, let's see, did I do this? All of that over 3 squared, or square root of 3 squared is now 3 minus 4. 3 minus 4. So this is going to be equal to, this part here is negative 1. And so we can view it as negative, and I'll just write it as 2 plus the square root of 3. 2 plus the square root of 3. So that's one possible value of x. And the other possible value of x, if we subtract the square root of 3, so then on the numerator we're going to have 2 minus square root of 3 minus the square root of 3. That's 2 minus 2 square roots of 3 over, we could write this as negative 4 plus 2 square roots of 3. 2 square roots of 3. The first thing we might want to do is just divide the numerator and the denominator by 3. I swapped these down here to divide the numerator and the denominator by 2. So this is equal to 1 minus the square root of 3 over negative 2 plus the square root of 3. And now we can rationalize this by multiplying it by negative 2 minus the square root of 3 over negative 2 minus the square root of 3. And what do we get here? What do we get here? So this gives us, so in the denominator, we're going to get, so this is going to be equal to, in the denominator, we're going to have negative 2 times negative 2 is 4. 4 minus 3. So we just get a 1. So this is equal to a 1 in the denominator. The numerator, 1 times negative, so let me just multiply 1 times negative 2 minus square root of 3. So it's negative 2 minus the square root of 3. And then the negative square root of 3 times negative 2 is plus 2 square roots of 3. And then negative square roots of 3 times negative square roots of 3 is plus 3. And so you have 3 minus 2 is 1. And then 2 roots 3 minus a square root of 3 is plus the square root of 3. So our two possible this is kind of exciting. This was an unbelievably hairy problem. Unbelievably hairy. And if any of y'all know a faster way to do this problem, let me know. I've thought a lot about it a lot. It doesn't seem like there is a faster way to do this problem. But my possible x values are negative 2 plus square root of 3 or 1 plus the square root of 3. Now, we have to be careful. If it wasn't enough that we got this far, we did so much work, we finally got these answers, we have to be very careful. Because both of those are options. This is one of the options, and then this is the other option. So, and once again, these are those multiple correct choice answers. So you can actually select more than one answer here. Or you need to select, maybe need to select more than one answer. So you might, after doing all of that work, say, oh, finally, OK, bam and bam. But be very careful. Remember the context. Remember the context of the problem. These sides had to be positive. And if you put this number in here, all the sides will not be positive. In particular, if x was 2 plus the square root of negative of this value right here, this value over here is going to be, I don't know, 3 point something something. And if you took the negative of that and you put it right here for c, you're going to get a negative distance for c. And c cannot be negative. It's the length of a side of a triangle. So A is not a valid choice. So these guys are really trying to trip people up. The correct answer is only B. That was tiring. So in problem 44, once again, we have the exact same setup that we had in problems 42 and 43. But now they're asking us the number of a in t sub p such that the determinant of a is not divisible by p. Well, we've already done some work in problem 43 in figuring out some set of the members that are divisible by p. So why don't we just figure out the total number of members of t sub p, and then subtract the total members that are whose determinants are divisible by p, and then we'll get this answer right over here. So what's the total members in t sub p? Well, for a, I have p possible choices, right? If I'm picking between up to p minus 1, but I'm including 0, there's actually p possible choices. So I have p possible choices for a, p possible choices for b by the same logic, and p possible choices for c. So I have p to the third possibilities. So they're total of p to the third members in t sub p. Now, what did the last problem tell us? This was number 43. It told us the members, maybe I should write it this way, the number of members, number of a's, such that the trace of a, this was the language they used in the last video or the last problem, such as the trace of a not divisible by p, but the determinant of a is. And we got the answer. As p minus 1 squared. Now, if you remember that problem, and even just to do that problem, we had to, when we thought about this statement, such that the trace of a is not divisible by p, we figured out that this was exactly equal to saying that a does not equal 0. So one way to view the result of problem 43 is if you assume that a is not equal to 0, there are p minus 1 squared members of t sub p where the determinant is divisible by p. So this is starting to get we're starting to count some of the a's whose determinant is divisible by p. But these are only the matrix a's whose a entry is not equal to 0. So if we want to count all of them, we have to also count the ones where a does equal 0. So where a does equal 0. So let's think about that case. We can figure out how many matrices there are where a does equal 0 and the determinant of a is divisible by p. Add it to that. Then we have the total number of a's that are whose determinants are divisible by p, and we can subtract that from the total number of possibilities, and hopefully we'll get one of the answers up here. So let's think a little bit about what will the determinant look like over here. So in this situation, the determinant of our matrix will be, it's a squared, it's a times a minus b times c. A squared minus bc. Now we're assuming that a is equal to 0. If a is equal to 0, it's equal to negative bc. And we need to think about how is this going to be a multiple, or how is this going to be divisible by p. So this has got to be equal to some multiple of p. So the first thing, you just think about b's and the c's. They are both non-negative. So this value right here cannot be negative. So if when you put a negative sign there, it cannot be positive. So it can't be any positive multiples of p. It could be 0, so we could have negative bc. We could have negative bc is equal to 0, which is equivalent to saying that bc is equal to 0. That's one possibility, where it equals 0 times p. That's still a multiple. Or maybe it could be negative. Maybe we could have negative bc is equal to negative 1 times p. But when you think about it here, if this was true, that would mean that bc is equal to p. And so b or c would be factors of p. Now we know that p is a prime number. Its factors are only 1 and p. B and c, I mean, one of these guys could be 1, but then the other guy would have to be p. They can't be p. They only get as high as p minus 1. This is not an option. So the only possibility, if a is equal 0, for the determinant of capital A to still be divisible by p is for bc to be equal to 0. So let's think about how many possibilities there are over here. So let's think about all of the combinations. So there's the one situation where b and c are equal to 0. B and c is equal to 0. Now let's think about the other ones. There's one where b is equal to 0 and c isn't. BC will still equal 0 in this situation. So how many possibilities are there? How many possibilities are there for this? Well, b is equal to 0. C over here can be any value, although we've already considered the case where c is equal to 0. So it can be any value so that we don't double count, any value where c does not equal 0. So it could be 1 through p minus 1. Or another way to think about it, there's p minus 1 possibilities. Now let's think about c is equal to 0 and b isn't. Well, exact same logic. Once again, we don't want to double count them both being equal to 0. So let me write it. And c isn't, well, we're saying it isn't 0, so we're actually already putting that constraint there. So it has p minus 1 possibilities. So how many total possibilities do we have where the determinant of a is equal to 0 and a is equal to 0? So we have 1 here. We have one possibility here, then p minus 1 and p minus 1. So our total possibilities are p minus 1 plus p minus 1 plus 1, which is 2p minus 2 plus 1, which is 2p minus 1. 2p minus 1 incremental possibilities when a is equal to 0 for the determinant of a to be divisible by p. So that's what we just got in this video. In the last video, we had p minus 1 squared possibilities when a does not equal 0. So if we want the total number of a's where the determinant of a is divisible by 0, we can add the number that we got in the last video to the number we just got. So let's do that. So if I were to rewrite this over here, this is equal to p squared minus 2p plus 1. And then I want to add this 2p minus 1 here. So plus 2p minus 1 plus 2p minus 1. And what do I get? These cancel out. These cancel with that. And these guys cancel out. So there's a total of p squared possible a's where the determinant of a divisible by p. Now, we're very close, but this isn't what they're asking. They want the total members that where the determinant of a is not divisible by p. So all we have to do here is take our total membership, which is p to the third. Take our total membership, which is p to the third, and subtract from that the members whose determinants are divisible by p. And we just figure that out. We subtract p squared. And now we'll get a's, the number of a's where determinant of a not divisible by p. Now let's see if that's one of the choices. And it is D, p cubed minus p squared. Let f, g, and h be real valued functions defined on the interval 0 to 1. And it includes the boundaries 0 and 1. That's what the brackets tell us. It wouldn't include the boundaries if we had parentheses. And then they define the functions. F of x is equal to e to the x squared plus e to the negative x squared. G of x looks very similar to f of x, except we have this x out here in front of the first term. And then we have h of x, which looks very similar to g of x and f of x, except it's got an x squared term right over there. And then they tell us if a, b, and c denote respectively the absolute maximum of f, g, and h on the interval, then so a is the maximum of f, b is the maximum of g, and then c is the maximum of h. And then they have a bunch of choices that compare the maximum values. Now, the first thing that may or may not jump at you, just looking at these equations over here. Now, we're over the interval 0 to 1. And let's just look at the functions themselves. Let's just look at the functions themselves. The difference is this one you could view has a 1 coefficient out front. This has an x, and this has an x squared. So over that interval, how are these functions going to relate? Over that interval, we know that over the interval from 0 to 1, over the interval from 0 to 1, we know that x squared is going to be less than or equal to x, which is going to be less than or equal to 1. They all equal each other at the right interval, at actually being equal to 1. So this is going to be less than this, which is going to be less than that. And these are all positive values. And the rest of the functions are the same. This is the same as that. That's the same as that. And that is the same as that. So over the interval, we know that h of x is going to be less than or equal to g of x, which is going to be less than or equal to f of x, which is going to be less than or equal to f of x. That just comes straight out of this coefficient is going to be less than or equal to this coefficient, which is going to be less than or equal to 1 over the interval. Now, with that said, let's actually try to figure out the maximum value. So I'll start with f. I will start with f. So f of x, let me just try it at the boundaries. f of 0 is equal to e to the 0 plus e to the 0 squared plus e to the negative 0 squared. That's just e to the 0 plus e to the 0, which is 1 plus 1, which is 2. And then f of 1 is e to the 1 plus e to the negative 1. This is e to the 1, or just e, I should say, plus e to the negative 1. Now, this is clearly larger than that. E is 2.71, keeps going. E to the negative 1, that's still going to be a positive number, obviously. So this, between the two endpoints, this seems to be a candidate for the maximum point. We don't know that's the maximum point because the function might have done something funky in between. So let me draw axes. I can draw a straighter line than that. So we know at 0, we took on the value 2. And at 1, we took on the value e plus 1 over e plus 1 over e, or e to the negative 1. So that's that value right over there. Now, we don't know what the function did in between. This would be the maximum point. This is the maximum point if the function did something like this. If it's constantly increasing the entire time, this would be the maximum point. It would not be the maximum point if the function looks something like that. And the way we can tell what the function is doing is we can take the derivative of f, which tells us the slope at any point over this interval. And if the derivative is constantly positive, that means we always have an upward slope. If the derivative is not always positive, then we have something like this, and then we can look for, actually look for that actual maximum point. So let's calculate the derivative. So f prime of x is equal to, see, derivative of e to the x squared is 2x e to the x squared, just using the chain rule. Derivative of e to the negative x squared is negative 2x e to the negative x squared. And let's see, we could factor out, this is equal to 2x e to the negative x squared times So if you divide this by e to the negative x squared, that's like multiplying it times e to the x squared. So this becomes e to the 2x squared minus 1. Minus 1. Now our question is, this is the slope over the interval. What is this doing at any point? Well, this value right here, this right here is always going to be greater than or equal to 0. It'll be 0 at the left-hand interval. Remember, this is the slope. The slope is 0 at the left-hand interval, which tells us it's either a maximum or a minimum point. But then it's going to be positive after that, because this is going to be a positive value, and that this is going to be a positive value. Remember, negative exponent does not mean a negative number. It means a fractional value. It's going to be 1 over e to the x squared. So this is always going to be greater than or equal to 0. And so we need to figure out, is this always greater than or equal to 0? So we want to figure out, is e to the 2x squared minus 1 greater than or equal to 0 over the interval? Which is the same thing as asking, is e to the 2x squared greater than or equal to 1 over the interval? I just added 1 to both sides of this inequality. And that's the same thing as asking, you can take the natural log of both sides. The natural log of this is 2x squared. The natural log of 1 is 0. So is 2x squared greater than or equal to 0 over the interval? Well, yeah, sure. It's going to be equal to 0 at x is equal to 0. But then after every other value, as it approaches 1, it'll be positive. So this is true. This is true. So this thing is always going to be greater than 0 over the interval, which tells us that the two parts of the derivative are always going to be greater than or equal to 0. So the derivative itself, the slope of the function, is always greater than 0. So always greater than 0 over the interval, I should say. Always greater than or equal to 0 over the interval from 0 to 1, which tells us that the slope is never negative, which tells us, and actually we know that the slope is 0 at 0. So that tells us that the graph looks something like this. The graph looks something like this, which tells us that the right endpoint, that f of 1, when x equals 1, f of 1 is the maximum point. So this indeed is equal to a. So we can actually write this here. F of x is less than or equal to a. Now let's think about h of x and g of x. So f of 1 was its maximum point. But g of 1, if you take g of 1 or h of 1, it'll evaluate to f of 1. Because if you put a 1 here, let's do that. Let me just do it to make it clear. So so we already evaluated f of 1 right over there. G of 1 is equal to, let me make sure we can see so g of 1 is equal to 1 times e to the 1 plus e to the negative 1. That's g of 1, which is the same thing as f of 1. So this is also equal to a. And h of 1 is the same thing. It's 1 squared, which is 1, times e to the 1 plus e to the negative 1, which is also equal to a. So what do we have a situation here? We know that h of x over the interval is less than or equal to g of x, is less than or equal to f of x, which is less than or equal to a. And actually, the only point where they all equal each other is at x is equal to 1. If this right here is f of x, g of x is going to look something like this, and h of x is going to look something like this. H of x might look something like that. And so they all finally equal each other. The only place they equal each other is at a, which is the maximum of f. So that also has to be the maximum of g and h, because they can both get to that value, and they can't get to any value higher than that. That's an upper bound on them. So this is also equal to b. Remember, b is just the maximum of g, and it's also equal to c, which is the maximum of h. So a, b, and c are all equal to each other, or we can say choice D. The value of the limit as x approaches 0 of 1 over x to the third times the definite integral from 0 to x of t natural log of 1 plus t, all of that over t to the fourth plus 4 dt is. Now, when you see an integral like this, your first temptation is to try to solve the integral. Try to find the antiderivative of this expression here. And you might try to experiment maybe with inverse trig functions. Maybe arctangent looks tempting over here, but you have this natural log. Maybe you could do it with integration by parts. But very quickly, or maybe not so very quickly, you'll realize that this is a nearly impossible integral to solve, or to simply solve using analytical methods. But lucky for us, this problem isn't just about solving this integral. It's actually about evaluating this limit. And if we rearrange this expression a little bit, it might become a little obvious to you how we can approach this problem. So this is the limit. This is the limit as x approaches 0 of, let me write this in the numerator, because this could be multiplying by 1 over x to the third is the same thing as dividing by x to the third. So this is the integral from 0 to x of t natural log of 1 plus t, all of that over t to the fourth plus 4 dt, and all of that over x to the third. And now this is probably ringing bells in some of your brains. And what we see here is, OK, we don't know how to evaluate this integral over here. But what does this integral approach as x approaches 0? What is the limit of this numerator expression as it approaches 0? Well, you're going to get, so let me just write it, the limit as it approaches 0. So the limit as x approaches 0 of 0 to x, all of that stuff in the side dt, is going to equal the integral from 0. Is going to approach the integral from 0 to 0 of all of that stuff dt. And an integral, a definite integral from 0 to 0, we're not moving it all along the horizontal or the t-axis. And so this is just going to be 0. And if we do the same thing in the denominator, that's much simpler. If we do the same thing in the denominator, the limit as x approaches 0 of x to the third, that's clearly also going to be 0. So we took the limits of the numerator and the denominator, and we got 0 over 0. That's the indeterminate form. And so now the bell should be ringing very loudly in your brain and screaming L'Hopital's rule. L'Hopital's rule. L'Hopital's rule. And I've done several videos on this in the calculus playlist. But this just tells us if we evaluate the limit of the numerator as it approaches 0 and the limit of the denominator as it approaches 0, and we get an indeterminate form, then this limit is going to be the exact same thing, assuming the limit exists, of the limit as x approaches 0 of the derivative of this expression over the derivative of this expression. Now let's do the denominator first, since that's easier. What's the derivative of x to the third? Well, that's just 3x squared. And what's the derivative of the numerator? And just as a reminder, and I'm just going to break out the fundamental theorem of calculus, the derivative with respect to x from some constant to x of f of t dt is just equal to f of x. You're kind of undoing the integration here. You just get f of x. It's just a function with respect to x. So the derivative of this with respect to x is just going to be this function with respect to x instead of t. So it's going to be x natural log, that was an ugly natural log of 1 plus x, all of that over x to the fourth plus 4. Now, when we try to evaluate the limit here, what happens? If we do the numerator, if we do the same thing we did up here, this numerator still evaluates to 0. You get 0 times natural log of 1. That's 0 as well. So that's all 0. The denominator still evaluates to 0. So we have indeterminate form again. So we might be tempted to just go straight, do L'Hopital's rule again, take the derivative of the numerator, and then take the derivative of the denominator. And that would work. But you can, or maybe you'll see that this is a pretty hairy thing to take a derivative of. And maybe we might have to take a derivative again after that. So this could get very, very, very hairy. So instead of just straight up just taking a derivative of the numerator and derivative of the denominator again, let's see if we can simplify this a little bit. And we can. So this is the same thing. This is equal to the limit as x approaches 0. I'm just going to put the x to the fourth plus 4 in the denominator. So it's x natural log of 1 plus x, all of that over this 3x squared, all of that over 3x squared. And I'm just, if I'm dividing by something and dividing by something else, that's just like dividing by that first thing. So this is x to the fourth plus 4. I just put this in the denominator. And we can simplify this. We can divide the numerator and the denominator by x. And now let's try to evaluate this limit. As x approaches 0 in the numerator, we get natural log of 1. So that's 0. So this is approaching 0 over. And if we do in the denominator, we have 3 times 0 times 4. So that's going to be 0. Once again, indeterminate form. So now let's apply L'Hopital's rule again. But we can apply it on a simpler expression, on natural log of 1 plus x over 3x times x to the fourth plus 4. So let's do that. So this is going to be equal to, assuming the limit exists, this is equal to the limit as x approaches 0 of the derivative of the numerator. The derivative of natural log of 1 plus x, that's just 1 over 1 plus x, over the derivative of the denominator. We just have to do a little product rule here. Derivative of the first function is derivative of 3x is just 3 times the second function, which is x to the fourth plus 4, plus the first function, 3x, is just the product rule, times the derivative of the second function. The derivative of this is 4x to the third. 4x to the third. Now, when we approach 0, what happens to this value? What does the numerator and the denominator approach? The numerator approaches 1 over 1 plus 0, or just 1. The denominator approaches 3 times 0 plus 4. 3 times 4 plus, this is just going to be 0, plus 0. So this is equal to 1/12. And we're done. This crazy looking limit with this integral that we couldn't solve is just equal to 1/12. So thank goodness we had L'Hopital's rule, so we didn't have to actually solve this, take the antiderivative of this expression. The value of the limit as x approaches 0 of 1 over x to the third times the definite integral from 0 to x of t natural log of 1 plus t, all of that over t to the fourth plus 4 dt is. Now, when you see an integral like this, your first temptation is to try to solve the integral. Try to find the antiderivative of this expression here. And you might try to experiment maybe with inverse trig functions. Maybe arctangent looks tempting over here, but you have this natural log. Maybe you could do it with integration by parts. But very quickly, or maybe not so very quickly, you'll realize that this is a nearly impossible integral to solve, or to simply solve using analytical methods. But lucky for us, this problem isn't just about solving this integral. It's actually about evaluating this limit. And if we rearrange this expression a little bit, it might become a little obvious to you how we can approach this problem. So this is the limit. This is the limit as x approaches 0 of, let me write this in the numerator, because this could be multiplying by 1 over x to the third is the same thing as dividing by x to the third. So this is the integral from 0 to x of t natural log of 1 plus t, all of that over t to the fourth plus 4 dt, and all of that over x to the third. And now this is probably ringing bells in some of your brains. And what we see here is, OK, we don't know how to evaluate this integral over here. But what does this integral approach as x approaches 0? What is the limit of this numerator expression as it approaches 0? Well, you're going to get, so let me just write it, the limit as it approaches 0. So the limit as x approaches 0 of 0 to x, all of that stuff in the side dt, is going to equal the integral from 0. Is going to approach the integral from 0 to 0 of all of that stuff dt. And an integral, a definite integral from 0 to 0, we're not moving it all along the horizontal or the t-axis. And so this is just going to be 0. And if we do the same thing in the denominator, that's much simpler. If we do the same thing in the denominator, the limit as x approaches 0 of x to the third, that's clearly also going to be 0. So we took the limits of the numerator and the denominator, and we got 0 over 0. That's the indeterminate form. And so now the bell should be ringing very loudly in your brain and screaming L'Hopital's rule. L'Hopital's rule. L'Hopital's rule. And I've done several videos on this in the calculus playlist. But this just tells us if we evaluate the limit of the numerator as it approaches 0 and the limit of the denominator as it approaches 0, and we get an indeterminate form, then this limit is going to be the exact same thing, assuming the limit exists, of the limit as x approaches 0 of the derivative of this expression over the derivative of this expression. And let's do the denominator first, since that's easier. What's the derivative of x to the third? Well, that's just 3x squared. And what's the derivative of the numerator? And just as a reminder, and I'm just going to break out the fundamental theorem of calculus, the derivative with respect to x from some constant to x of f of t dt is just equal to f of x. You're kind of undoing the integration here. You just get f of x. It's just a function with respect to x. So the derivative of this with respect to x is just going to be this function with respect to x instead of t. So it's going to be x natural log, that was an ugly natural log of 1 plus x, all of that over x to the fourth plus 4. Now, when we try to evaluate the limit here, what happens? If we do the numerator, if we do the same thing we did up here, this numerator still evaluates to 0. You get 0 times natural log of 1. That's 0 as well. So that's all 0. The denominator still evaluates to 0. So we have indeterminate form again. So we might be tempted to just go straight, do L'Hopital's rule again, take the derivative of the numerator, and then take the derivative of the denominator. And that would work. But you can, or maybe you'll see that this is a pretty hairy thing to take a derivative of. And maybe we might have to take a derivative again after that. So this could get very, very, very hairy. So instead of just straight up just taking a derivative of the numerator and derivative of the denominator again, let's see if we can simplify this a little bit. And we can. So this is the same thing. This is equal to the limit as x approaches 0. I'm just going to put the x to the fourth plus 4 in the denominator. So it's x natural log of 1 plus x, all of that over this 3x squared, all of that over 3x squared. And I'm just, if I'm dividing by something and dividing by something else, that's just like dividing by that first thing. So this is x to the fourth plus 4. I just put this in the denominator. And we can simplify this. We can divide the numerator and the denominator by x. And now let's try to evaluate this limit. As x approaches 0 in the numerator, we get natural log of 1. So that's 0. So this is approaching 0 over. And if we do in the denominator, we have 3 times 0 times 4. So that's going to be 0. Once again, indeterminate form. So now let's apply L'Hopital's rule again. But we can apply it on a simpler expression, on natural log of 1 plus x over 3x times x to the fourth plus 4. So let's do that. So this is going to be equal to, assuming the limit exists, this is equal to the limit as x approaches 0 of the derivative of the numerator. The derivative of natural log of 1 plus x, that's just 1 over 1 plus x, over the derivative of the denominator. We just have to do a little product rule here. Derivative of the first function is derivative of 3x is just 3 times the second function, which is x to the fourth plus 4, plus the first function, 3x is just the product rule, times the derivative of the second function. The derivative of this is 4x to the third. 4x to the third. Now, when we approach 0, what happens to this value? What does the numerator and the denominator approach? The numerator approaches 1 over 1 plus 0, or just 1. The denominator approaches 3 times 0 plus 4. 3 times 4 plus, this is just going to be 0, plus 0. So this is equal to 1/12. And we're done. This crazy looking limit with this integral that we couldn't solve is just equal to 1/12. So thank goodness we had L'Hopital's rule, so we didn't have to actually solve this, take the antiderivative of this expression. Let P, Q, R, and S be the points on the plane with position vectors negative 2i minus j, 4i, 3i plus 3j, and negative 3i plus 2j respectively. The quadrilateral PQRS must be a. So let's just graph each of these position vectors, or graph the points that they're specifying. So let me draw my coordinate axes right over here. So that would be, this is my vertical. Let me draw, I could draw a straighter line than that. There you go. That's about as good as I can do. Let me draw the horizontal. That's a better job, I think. And then let me mark it off. Let's see, we go as high as 4. We go up to 4i. So 1, 2, 3, 4. We go as low as negative 2i. So 1, 2. Just making sure. Let me make it a little bit even because we're going to have to figure out the shape of whatever we draw. Then we're going to go up 3. We're going to go up 3. 1, 2, 3. And I think that, and we actually go down 1 as well. So I think that'll give us, and we could keep marking them off if we wanted to. But we don't need to based on the positions that have been specified. So let's draw these vectors. So let's draw vector p first. Negative 2i minus j. So negative 2i, I is along the horizontal, or you can imagine as the x-coordinate. So negative 2i minus j. So it is this position vector right over here. If we put it in standard form, starting with its base at the origin. It's that position vector. But it's specifying that point over there, which is the coordinate negative 2, negative 1. So that's, let me just write it down. Negative 2, negative 1. Now let's do 4i. So 4i is literally, we just go, that's just 4 in the x direction. 1, 2, 3, 4. There's no y component, or there's no j component, no vertical component. So it specifies that position right over there, or it specifies the point 4, 0. Then we have 3i plus 3j. So 1, 2, 3, 1, 2, 3. That is that point right there. The position vector specifies that point, or specifies the point 3, 3. And then finally, we have negative 3i. Let me do this in another color. Negative 3i, so 1, 2, 3, plus 2j, 1, 2. So right over there. So that is that last position vector. And it's specifying the point negative 3, 2. And they want to know what's the quadrilateral made by these 4 positions. So let's draw it. Let's connect the dots. So this is P, go to Q. It gets us that line right over there. Then from Q to R, we're going to go like that. We're going to go like that. And then from R to S, we're going to go like that. And then actually it's going to go a little bit more. It's going to go like that. And then from S, oh, sorry, that's from S to R, and then R to, and that's from, sorry, that's from R to S, and then S to P is going to be like that. So just eyeballing it, it's clearly not a square. It's clearly not a square. It's clearly not a rectangle. It's coming off at different angles. It's clearly not a rhombus. A rhombus would have all of the same sides. So a square would be all 90 degrees. Would be all the same sides and all the angles are 90 degrees. That would be a square. It's clearly not a square. A rectangle would be all the angles are 90 degrees, but the sides, 2 sides are going to be the same and the other 2 sides are going to be the same. This is not, these do not look like 90-degree angles. Now, the last one, and you could try if you want. I mean, just eyeballing it, it's pretty clear these aren't 90-degree angles. But if you wanted to, you could find the slope of this and find the slope of that line. And if they're not the negative inverse of each other, then they're not perpendicular and they're not coming at 90-degree angles. And so the last one is, are they a rhombus? A rhombus is a parallelogram while the sides are the same. So a rhombus would look like that. Clearly not a rhombus. These sides are clearly much longer than those sides over there. Now, just from deductive reasoning, it looks like the answer is A. It's a parallelogram. But we can verify it. We can make sure that in order for this to be a parallelogram, these 2 sides have to be parallel, and these 2 sides. And these 2 sides have to be parallel. Or another way to think of it, they would have to have the same slope. So we could verify it. If we were taking this on an exam under time pressure, we would just cross these out and it looks pretty good. We would just go with A. But let's just verify it. So what's the slope? What's the slope down here? What's the slope down here? So it's change in y over change in x. So 0 minus negative 1, 0 minus negative 1 over 4 minus negative 2. Or this is equal to 1 over 4 minus negative 2 is positive 6. This is 1/6. Or another way to think about it, we ran 6 and we only rised 1. This is 1/6. Now what happens over here? Well, it's the same thing. We're going from negative 3 to 3. So we're running 6. So we say 3 minus negative 3 is equal to 6. And how much did we rise? We have 3 minus 2, which is equal to 1. So this is also a slope of 1/6. So these 2 lines are clearly parallel. And now let's do it for these other 2. What's the slope over here? what's the slope over here? And actually, you could just do rise over run. Rise over run. So that's exactly what we were doing before, but just to give you the taste for everything. So we ran. To go from here to here, we have to move to the right 1. So we run 1. And how much do we rise? Well, we had to go down 3. We had to go down 3. So it's -3. So the slope here is -3. And what about here? To go from this point to this point, we went to the right 1. So we ran 1. And we had to go down. We started at 2. We ended up at -1. We had to go down 3. So the slope here is also -3. So these lines are also parallel. So we're definitely dealing with a parallelogram, which is neither a rhombus nor a rectangle.